Assalamu alaikum students. Today we will study our next topic. That topic name is interpolation, and what is polynomial interpolation, and also what is Lagrange interpolation. So let's start it. So first of all, I will tell you what is an interpolation and what does it do and what are the benefits of interpolation. Okay, the interpolation, the process is the process of finding the unknown value from the given values or known points is called interpolation. For example, I will give you the practical example of this interpolation, and we also must have the concept of extrapolation. So extrapolation is basically process of finding the unknown value of y for a given value of x lying outside the table of values of x is called extrapolation. So for example, we have this set of values like for x we have this set of values. For x we have x0, x1, x2 and so on, and last column is xn, and the images of xn is for example, if it is f of x, then I would say the image is y, so that if the image of x0 is y0, the image of x1 is y1 and y2 and so on, yn. So this is what we called a given set of values. The process of finding the value, unknown value, like if I would say xi is the intermediate point and you have to find out y interpolation, and if xi remains outside of the table, like if I would say xn plus 3, you have to find yn plus 3 and you don't know what is n plus 3, so xn plus 3. So that process is known as extrapolation, or we can say the prediction of the future. The best example for extrapolation is prediction of future. Okay, practical example. Let us consider the computation of the trajectory of a rocket missile or a missile flight, where we solve the Euler's dynamical equation of motion, because for having the particle or any object to study its path and to study its position vector and other parameters, we use two systems. One is Euler's dynamical system and equation of motion, and the other one is Lagrange dynamical system equation of motion. So in this we solve the Euler's dynamical equation of motion to compute its position and velocity vector and various parameters, position and velocity vector, and also its time. At the specific times we study these parameters at the specific times. During the flight, we require the position and velocity vector at some other intermediate time. Like if it is at rest, if at t equals to 0, the position vector is given and the velocity vector and other parameters are given, and at the end of its journey, it's also position vector and velocity and all the final position is also given. But within the, for example, in the intermediate time, in this point, like t is equal to 10 seconds, you have to find out its position vector and velocity. So that process is known as interpolation. So at some intermediate times we don't need to now interpolation has the benefit that by solving the very time consuming and very complicated Euler's dynamical equation of motion to get its position and velocity vector in the intermediate time, we just use the simple technique of interpolation to get its position and or any parameter, velocity vector or any parameter, to get its within the interval. Within interval we can find out with a very efficient method like Lagrange interpolation. Depends upon that what is the nature of the function, and also the Newton's divided difference and all that. So now we will study the polynomial interpolation. So instead we can use the best known interpolation technique to get the desired values. So I hope that you understand this concept now. Okay, so now what is the polynomial interpolation and why it is required? It is required because we have discrete, if we have interpolation is required if we have discrete data instead of a continuous function, and only the discrete values are given, and we have to find out the intermediate values within that interval. Then this interpolation is very efficient. And then polynomial interpolation has the benefit that derivatives and integrals of polynomials are easy to determine. Okay, and also by default it is a polynomial is a continuous function, so we have less complications, and we get the results with the we get the approximations with a higher accuracy. So what is the type of polynomial interpolation? Polynomials are of this type, and we construct the table regarding this. I am doing it again. So if we have x1, x2, x3, pen starts from this to so on xn. The function values images are f1, f2, f3 to so on fn. A polynomial that satisfies this equation, this interpolation, is called interpolating polynomial. That is p of x basically. I will tell you in the Lagrange interpolation that what is this interpolating polynomial I am talking about. And the points xi are known as interpolation nodes. So polynomial interpolation is just like that. Pn of x is equal to a naught plus a1x plus a2x square. Simple polynomial interpolation is like that. It's just a polynomial function, but in the further methods I will tell you what is the interpolating polynomial. So a good interpolation polynomial needs to provide a relatively accurate approximation over an entire given interval. Now we move towards the Lagrange interpolation, and in the Lagrange interpolation we find approximating polynomials that can be determined by specifying certain points on the plane through which they must pass. For example, we consider the polynomial of degree 1 that passes through the distant points, like you have only 2 points, x0 and y0 and x1 and y1. So the interpolating polynomial, consider this linear polynomial because it arises to only equation of line. So p of x and the polynomial will be linear polynomial. So the Lagrange interpolation for this polynomial of degree 1 is x minus x1 divided by x0 minus x1 into y0, or f of x0, plus x minus x0 into x1 minus x0 into y1. So if we consider this one is interpolated at x0, so this is known as L0 of x, and this is interpolated at this point x1, so this is known as L1 of x. So basically it is in the form of L0 of x y0 plus L1 of x y1. So if we consider this at x0 and x1, then p of x0, if we say this equation as a, and if I replace instead of x is x0, then for this it will become this term, second term will become x0 minus x0, that makes it 0, and this makes it x0 minus x1 divided by x0 minus x1, so it becomes 1 into y0 plus 0 into y1, that makes it y0. So it becomes y0. Yes, is to at certain specific points. Similarly, if I replace this equation with x with x1, then x1 minus x1, that makes it 0. So 0 minus y0 plus x1 minus x0 divided by x1 minus x0, that makes it 1. So it becomes to it converts it into a y1, and similarly we can replace here as x equals to x0, and also we can replace it x equals to x1, and also we can replace here in the similar way. So this is basically linear polynomial. We start with the very basic concept, and if I want to suppose the two 3 points now. So L0 and L1 was the Lagrange interpolating polynomial. So if we have 3 points now, x0 y0, x1 y1, and x2 y2. So now this will give a rise to the 3 Lagrange polynomials. So L0 of x is equal to x minus it means x0 is the reference point here, so ignore the x0 in the numerator and do the difference with the rest of the points x1 and x2. X minus x1 into x minus x2 divided by, now it is the x0 is the reference point here, so x0 minus x1 and x0 minus x2, so that is Lagrange L0. Similarly, L1 of x is if here x1 is the reference point, then the Lagrange polynomial, interpolating polynomial, will be ignore the x1 and write down the rest of the points. So x minus x0 and x minus x2 and x1 minus x0, similarly x1 minus x2, and also third Lagrange polynomial is L2 of x if we start from 0. So again here x2 is the reference point, so you write x minus x0 and x minus x1 divided by x2 minus x0 into x2 minus x1. So this will be written as P of x is equal to L0 of x into y0 plus L1 of x into y1 plus L2 of x into y2. For 3 points, this will be the interpolating polynomial. Okay, now we generalize this concept. If we have 4 points, then we will get 4 interpolating polynomials, and your Lagrange interpolating polynomial will become in the generalized form. And if we have n journal points of Lagrange, then what we will say? We will construct its generalized Lagrange polynomial. Okay, so we have n points and we want to take k as a random or reference point here. L n comma k of x is the general nth order Lagrange polynomial. That will be x minus x0 into x minus x1 into x minus x2 to so on. Last will be x minus xn divided by, if k is the reference point, then xk minus x0, xk minus x1, xk minus x2 to so on, xk minus xn. And if I want to write, because every term is multiplied, so I want to write it in the compact form. I will write it for some for addition. We use, if we want to use the addition in the compact form, then you use the symbol this sigma as summation. But if you want to use the product, you want to write the product in the compact form, then you write this pi, capital Pi. So these both symbols were introduced by Lagrange. Product summation and x minus xn divided by xk minus xn, where if I want to vary these if I write it I, and if I write it as I. So I varies from 0 to n, and in MATLAB we use the starting point as 1. So be alert about that. And I must not be equal to k. So this is the Lagrange general order, nth order polynomial. And then we use this in the theorem, and the theorem is generalized theorem for polynomial is p of x is equal to f of x naught, that means y naught, into ln 0 of x plus f of x1 ln 1 of x plus to so on f of xn ln n of x. So I can write this in the compact form. So here it is sum, addition basically. So I write is summation f of xk, k is in the subscript, ln comma k of x, and k starts from 0 to n. So this is the theorem we apply in the last, after finding out the Lagrange polynomial, we apply these all Lagrange polynomials one by one, and we multiply with its respective y0 and y1 and y2, and then in the end we get the interpolating polynomial. So we will do its example in the online lecture. It's very easy and very interesting example.